Hello friends, uh, welcome to film screen radiography. Now let us learn some important points about intensifying screens. X-ray films are relatively insensitive to X-rays, and if used in isolation they would require unacceptably high levels of radiation to produce a satisfactory image. With an exception of intraoral dental radiography, the film used in clinical radiography is always used in association with intensifying screens, which convert the X-ray pattern or X-ray intensities into light. So, this intensifying screens are just a sheet of material which is same size as that of film. The screen This intensifying screen has a polyester base which is around 0.25 millimeters thick, on which coated a dense layer of fine phosphor crystals. Okay, this dense layer of fine phosphor crystals is around 0.1 to 0.1 to 0.5 mm thick, and the phosphor crystal is again 3 to 10 microns in size. The phosphor crystals are 10 to 5 microns in size, whereas the dense layer is 0.1 to 0.5 mm in thick. So, if this is the film, okay, on either sides of the film there is the what do we say, the emulsion. Okay, this is film, this is emulsion, then just above the emulsion there is a super coating. Okay, so this hole is the film. Okay, just above the film there is the intensifying screens. So this is the intensifying screen. In the intensifying screen itself there is first layer. So if I draw this here, the intensifying screen will have a thin layer of polyester base, and on either sides of the intensifying screen there is a dense layer which consists of fine phosphor crystals which are 5 to 10 microns in size, and these are bound by a transparent resin. These phosphor crystals will absorb the X-rays and emit light intensity which is proportional to the intensity of X-rays. So, they emit the light intensity proportional to the intensity of X-rays. This screen converts the pattern of X-ray intensities which are emerging from the patient into one of the light that is then recorded on the film. The photon absorption in the screen is determined by absorption coefficient of the phosphor material. So this absorption coefficient of phosphor material is very important. The traditional phosphor which is used in radiography is calcium tungstate, and this calcium tungstate is a material that emits blue light when irradiated with X-rays. The variation of mass energy absorption coefficient for calcium tungstate with photon energy is shown in this figure. So, on x-axis we have variation in absorption coefficient, and on y-axis photon energy is given. The coefficient is predominantly influenced by the tungsten. These small dotted lines is for tungsten, right? And this is for gadolinium oxysulfide. So, if you see that tungsten has atomic number of 74, and the K edge of tungsten is around 70 kilo electron volts. So, as a result, at around 70 kilo electron volts, absorption coefficient is least. So, superimposition of the spectra of 60 to 100 kilovolts X-rays demonstrates that the absorption coefficient is not optimally matched to the typical spectra used in radiography. With relatively low attenuation at the peak of the X-ray spectrum. So at the peak of X-ray spectrum, there is low attenuation and poor detection of characteristic radiation. The use of calcium tungstate has been right now superseded by the rare earth elements. The rare earth elements like gadolinium, they have the atomic numbers in the range of 57 to 70 and the K edges in the range of 39 to 61 kilo electron volts. The phosphors are most commonly used in intensifying screens are lanthanum oxybromide, lanthanum oxysulfide, gadolinium oxysulfide. The absorption coefficient of gadolinium is given in this picture. The phosphors incorporate some impurities or activators. These impurities or activators form the energy trap. The combination of the phosphor with the activators will produce the light spectrum that is specific of that material. Then sensitivity of the film should match the spectrum of emitted light. So here if you see the tungsten, calcium tungstate, because the KH coefficient is around 70 kilo electron volts. So at 70 you will see the absorption coefficient will increase maximally at the K edge. Right. Next, if you see some important points about the rare earth elements, the rare earth elements are not chosen just on the atomic number, but the rare earth elements are more efficient than the calcium tungstate elements. The rare earth elements are more efficient than calcium tungstate in converting the absorbed X-rays into the light. The two factors together which make the rare earth elements more sensitive than calcium tungstate screens is that the rare earth requires smaller exposure for conversion of same amount of X-rays into light as that of calcium tungstate, and the rare earth also this smaller exposure will result in decrease in or reduction in patient dose 2 to 3 times lower or lesser while producing the same quality of image. The X-ray film is usually double coated with emulsion on both the sides. The X-ray film is double coated with emulsion on both the sides. Each emulsion is in contact with the phosphor coating of the intensifying screens. So this is the phosphors. Each emulsion is in contact with phosphor coating of an intensifying screen. About 2/3 of X-ray radiation falling on the front of the screen is absorbed and about half of the X-ray radiation is converted into light. So about 2/3 of the X-ray radiation is absorbed by the phosphors. Sorry, there is a mistake. Okay, about 2/3 of the X-ray is absorbed by the phosphor, and this 2/3 of X-ray is converted into light. And among this whole light, about half of the light so produced travels forwards and exposes the near emulsion or the front of the emulsion. The rare screen absorbs about half of the X-ray radiation transmitted from the front screen into the back, and about 2/3 of the total fluence is absorbed by the two screens in combination. Light from the back exposes the rear facing emulsion. So light from the back will expose the rear facing emulsion, and light from the front will expose the front facing emulsion. Overall, 2/3 of the X-rays are converted to light. 2/3 of the total fluence or X-ray photons are converted to light. The screen materials are chosen that do not emit delayed fluorescence, because if there is delayed fluorescence, then this will result in memory of the previous exposure. On reloading the cassette, the previous image would be recorded on the new image and superimposed on the image of subsequent exposure. So delayed fluorescence materials which emit delayed fluorescence are not selected as intensifying screens. Thank you.